Today, on how it's made. Fly fishing reels. House paint. Weaving looms. And ice makers. Fishing reels date back to 12th century China. In the beginning, they were very basic devices, used only for storing extra line. But by the 1800s, craftsmen in Britain and America reinvented the reel when they gave it a drag system for landing feisty fish. These fly casters could hook the big one at any moment, and that's when a precision fishing reel will come in handy. To make a fly fishing reel, they start with a solid aluminum puck. The puck turns on a lathe as a computerized cutter contours it to shape it into a spool. A different tool machines a center hole. The focus then moves to the other side as another tool completes the spool shape. The dimensions must be exact if this fishing reel is to perform flawlessly. They drill holes to both reduce the weight of the spool and provide some ventilation for wet fishing line. They cut windows into the other side for an attractive look that further lightens the reel. Next, another aluminum puck is transformed into a frame for the spool and other parts. The frame goes into a bath of soapy water and plastic pellets, which rub the part clean. The final touch is a black oxide finish. They now transform this aluminum bar into feet, which will be used to mount the reel to the fishing rod. A laser engraves the company name onto these attachments. It also does a bit of custom engraving on the frame. A worker now inserts a bronze bushing into the center of the spool and uses hydraulic force to entrench it. He then positions a stainless steel ball on top of the bushing. He activates a press that drives the ball through it to expand the bushing to the correct internal dimension. Another worker applies a counterweight to one side of the spool. This bit of stainless steel will offset the weight of the spool handle. She installs the spool's magnetic locking mechanism. This molded polymer part has a tiny magnet inside. She applies a second magnet to it, followed by a release button. One final magnet and an aluminum cap, and this assembly is complete. She now installs part of the drag engagement system. It's this system that will create the necessary resistance on the fishing line for battling a big fish. She applies adhesive to screws and then uses them to attach the footing to the fly reel frame, using a screwdriver set to a specific torque. She then resumes the assembly of the drag system by placing a rubber O-ring in the frame's center groove. She installs the thrust-bearing ring, which can be rotated by the fly fisher to adjust the drag setting. And now it's time to attach the spool to the fishing reel frame. She turns it to check the drag setting and adjusts it to its starting point. She secures the setting by inserting a pin into the bearing. Then she removes the center locking screw temporarily to assemble the knob base to the thrust bearing. She reinstalls the screw and covers the assembly with the drag knob. She turns the spool for a final inspection, confirming that this fishing reel operates smoothly. And now, it's ready to put a positive spin on any fishing experience. A fresh coat of latex paint is a surefire way to spruce up a home. Latex is a term for acrylic or vinyl resins. Latex paint is water-based, so it has less odor than alkyd paint. It also cleans up without any harsh solvents. All you need is soap and water. The paint factory produces an uncolored base. The store then tints that base to the color ordered by the customer. Latex paint contains water, latex for adhesion, titanium dioxide, calcium carbonate, potassium, zinc for mildew resistance, and whatever additives the particular type of paint requires. For example, if it's paint designed for metal, a rust inhibitor. They pump the water into a large mixing tank. Then they add a thickening agent and stabilizer to prevent the ingredients from settling to the bottom of the tank and to the bottom of the can once the paint is packaged. A vacuum duct sucks up the waste. One at a time, all the ingredients except the latex go in. There's a specific mixing time after each ingredient because proper blending is critical for quality. Now they pump the tank's contents into another mixing tank that contains the latex. After 4 to 6 hours of blending, the industrial-size batch of paint base is finally ready. The factory subjects a sample from every batch to extensive quality control testing. This viscometer measures the thickness of the paint. This test assesses how well the dry ingredients have dispersed within the mix. This tells them whether the mix is blended well enough to move into the second tank containing the latex. Technicians also conduct color tests, adding recipes of liquid colorants to a gallon sample. This is to ensure the shade comes out exactly the way it's supposed to. To check if the paint covers well, they brush it onto test paper. The stripes provide a contrast so that any defects in the paint, such as foam or grit, will show. This test evaluates tint strength. Once the paint sample dries, they analyze its color properties with a machine called a spectrophotometer. Once the batch passes inspection, it proceeds to packaging. Latex paint contains about 60% water, which corrodes metal, so the steel cans are lined with an anti-rust coating. The cans run over a glue applicator, then over a label, which instantly sticks to the adhesive. The next stop is a filling machine. Each can sits on a scale that's positioned under a dispensing nozzle. Once the scale detects the correct net weight, it triggers the nozzle to stop. From the filling machine to a lid dispenser that drops a cover onto each can. Then it's onto what's called a lid press. As each can passes underneath, a row of cylinders gradually presses in the lid. The next machine, called a baler, attaches a curved handle made of steel wire. It locks the handle ends into metal discs on both sides of the can. The factory varies its formulations to produce paint in lusters ranging from flat to high gloss, and for interior and exterior use, making sure it's got every possible application covered. Looms for hand-weaving cloth have become increasingly sophisticated over time, but the basic concept still remains the same: weaving horizontal threads, called weft threads, through vertical threads, called warp threads, to create the patterns in the cloth. The loom lifts selected warp threads. The weaver passes the weft thread between the warp threads, then uses a beater to pack the weft tightly. They construct the loom's frame out of ash, which is strong enough to withstand the pulling of up to thousands of threads. Workers submerge the frame pieces in mineral oil to prevent the wood from drying out. They assemble the frame pieces with heavy-duty nuts and bolts, then mount high-strength plastic brackets for attaching the various components, such as the cloth beam, that grabs and moves the finished cloth. They wrap sandpaper around the beam's adhesive surface to grab the cloth without damaging it. Elsewhere, workers make the loom's cables out of high-strength stainless steel. These cables maneuver harnesses that lift and lower the warp threads. After cutting each cable to length, she forms a loop through a cable crimp. Then she locks the loop with this heavy-duty crimping tool. On one of the frame pieces, they mount a metal plate bearing the loom's model and serial number. They assemble the pulley system on which the harness cables run. They thread the plastic pulleys onto a steel axle and position the axle with steel discs called stop collars. A spring lever helps each harness lift its respective warp thread. After hammering a pin into each lever, they hook a wire to the pin. Then squeeze the wire closed so that it can't unhook. They attach a chain to an eyelet on one side of the spring lever. Shortening or lengthening this chain adjusts the tension of the harness. Like the pulleys, the spring levers go onto an axle across the loom's frame. Another loom component, called the warp beam, has holes which hold metal hoops that guide the warp threads. A brake drum on the side provides counterforce to keep the threads taut. At the front of the loom, they install foot pedals, called treadles. The weaver uses them to lift and lower the warp threads. Next comes the beater, which the weaver uses to pack the weft thread into the fabric. The pulley system for the harness cables goes on top. This computer-controlled device, called a dobby head, lifts and lowers the warp threads according to the programmed weaving pattern. Each harness cable hooks onto the dobby head, goes around one of the pulleys, and attaches to a hook on the harness. The factory checks every dobby head on a test loom to ensure the device outputs the programmed patterns correctly. Next, workers install the spring levers that help the harnesses lift the warp threads. Each lever hooks onto a spring, which attaches to a chain, which connects to a harness. They install the warp beam at the back of the loom. The weaver installs the hoops and warp threads on the warp beam. As the loom weaves, the cloth beam gently moves the emerging fabric forward. The weft thread is wrapped around a bobbin called a shuttle. This pattern requires a two-weft thread technique that uses a second shuttle suspended in front of the weaver. The loom keeps the threads evenly taut, producing a consistent and uniform weave, the hallmarks of a beautiful, quality cloth. Until the mid-19th century, Mother Nature was the only producer of ice, and the idea of man-made ice seemed preposterous. It was a Florida doctor who, in need of ice to cool feverish patients, invented the ice machine. The technology took a few years to refine, and then they were ready to chill. Today's commercial ice makers churn out ice on demand, allowing restaurants and other businesses to keep things cool at all times. To make one, machinery folds the edges of stainless steel sheets so they can be assembled into the ice maker frame and exterior panels. Meanwhile, copper uncoils over a roller, which removes the curl from the metal. A machine spiked with blades then punches the copper. In one action, it cuts numerous slits in the strip and slices it to the correct length. The notched strips are now ready to be assembled into a grid. This grid is part of the evaporator. It's here that liquid refrigerant will evaporate as it pulls heat from the water to freeze it into ice cubes. This copper tubing is central to that process. An automated arm bends it into a configuration called the serpentine, producing a coil that will fit on the back of the evaporator. As liquid refrigerant moves through it, it will draw heat out of the water. This machine flattens the tubing, giving it greater surface contact with the evaporator to facilitate heat transfer. Then, it's into a big washing machine to remove any oils or oxides on the parts. A worker now applies strips of tin silver solder to the evaporator's backplate. This acid solution will act as a bonding agent. He then places the evaporator, solder side down, on the serpentine tubing and locks the assembled parts in an iron rig. He hoists the rig into an oven to melt the solder strips between the backplate and tubing, fusing the parts together. Then, it's into an ultrasonic bath, where high-frequency sound waves clean off lingering contaminants. An inspector now examines the evaporator to confirm that the parts have been solidly fused. Next, he installs pipes on an ice maker side panel. These are the lines that supply refrigerant to the machine. He turns the assembly around and removes the caps on the compressor to connect it to a network of pipes. The compressor will force refrigerant through these pipes in a continuous cycle of heating and cooling to eventually produce ice. He brazes the joints to seal the connections. He attaches a fan to another side panel. It will blow cool air onto the radiator to cool the refrigerant and help convert it back into a liquid. Now he pumps the refrigerant into the system and measures the flow to ensure it receives a precise amount. Meanwhile, at another station, they assemble the ice bin. It's time to test this ice maker. Water flows continuously over the surface of the evaporator grid as the temperature inside the cells drops below freezing. Impurities like minerals are washed away as the water turns to ice, and the result is crystal clear cubes. Almost 3 kilograms in just 15 minutes. Finally, they install the front panel on the unit. This job is done, and it's time for a little liquid refreshment. On ice, of course. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.